Okay. Yesterday we talked about the first big problem in class, which was the tangent line problem, right? And the tangent line problem before the group exploration, how do you find the slope at one point? Guys, in your homework, for those of you that started, because that was homework last night, let's just start it. The very first, was it 2 or 3 questions? I think the first 2 questions. What were they about?
The first 2
Questions.
about
Velocity, rate. They were about velocity, they were about rate. What is a very popular formula, or a very common formula having to do with rate?
D equals
Sure, good. D equals, distance equals
rate times time.
time, good, and then rate. Distance equals rate times time. So if we were asking for total distance traveled without calculus, you would need a change in distance and a change in time. You would need not only a constant time, how much time to consider as far as how long they're traveling, but you would also need, do you remember from yesterday, what kind of rates, what kind of velocities can we deal with without calculus?
Just constant.
Constant. Constant velocities we can plug in. Constant velocity times a constant time. There we go, we have a constant as far as a value for the distance traveled. When is this not possible without calculus?
If you have to slow down at stoplights.
Okay, if the rate is changing, and how could you see the rate is changing? What would they have to give you for that rate? Some sort of, exactly, a function. If they give you a function, if v equals f of t, if you have some sort of function for velocity, so that when t is this, you have this velocity. When t is 2, you have a different velocity. T is 3, a different velocity. If the velocity is changing, it's not just a number, then I can't use calculus. So the tangent line problem, not only is it how to find a slope at one point, it's also, in context, slope is like rate. So it's also how to find the rate at one time, not over an interval. So you'll notice that as well when you go into homework, or you might have already noticed it. If they ask for the rate at one time, or they only give you one time, that needs calculus. And if they ask for a rate over an interval, where you know like a distance traveled over a certain time interval, that would be without calculus. Another way of looking at it. But tangent line problem, once again, this is one of the foundational problems of calculus. It's just applied and can be applied in so many different fields, so many different types of problems and situations. But we talked about that yesterday with our group exploration. We talked about how we were trying to zone in or zero in on, what was our point of tangency yesterday?
Of 2. Oh, wait. Oh, 1,
1, 1, right? So our point of tangency was 1, 1. So we were trying to zero in on 1, 1. Question, was this first line a tangent line? No. What's it called if it crosses through the graph at 2 points? A secant line. So we started finding secant lines, specifically the slopes of secant lines, at places that were removed from the tangent point. So we were trying to figure out what was going on at 1, 1. Remember that was 1 through going by point ones, I think. And then this was 1 over here. We were trying to find a tangent line at 1, 1, but we can't find the slope at one point without calculus, so we were using pre-cal and algebra 2, etc. to find the slope at some point removed, like 0.4, some point removed, like 0.9, or maybe it was 0.99. That actually a little bit closer, wouldn't it? We had a line through that one. We had a line at 1.1. We had a line at 1.01. We had a line at 1.0001, which would be like right there. And we were finding the slopes of all these different lines. And as we looked at the slopes of all those different lines, what allowed us to make the jump of, I bet the slope of the tangent line is this? What were we thinking? What one word? As we were looking at the slopes of the secant lines, what were we thinking that allowed us to make the jump of, I bet the slope of the tangent line is 2? Approaching. And what mathematical procedure, operation, concept does approaching go with? Limits. So we had to take that, long story short, the answer to our, the answer to our problem is to start with pre-cal, realize we can find a slope between 2 points, and then say, hey, let's go ahead and make the distance between these 2 points shorter and shorter and shorter and shorter to make the lines get closer and closer and closer and closer, so that we can see what the slopes of the secant lines are approaching. And so, how is it possible to find the slope of a tangent line? Well, we could experiment every time like you guys did in group exploration, and we could look at secant lines. Wherever the point of tangency is, wherever P is, we could take a point that's a little bit removed and then a little closer, a little closer, a little closer, a little closer. Technically, to be completely accurate, we should do it from both sides, from below and above. And we would look at all those slopes and say, hey, can I tell what the slopes seem to be approaching? So we have to use limits and we have to use approaching. Problem number 2, notes, area problem. You just have to sketch it. Area problem. Long story short, what if you have an irregular area? What do we mean by irregular? What would be a regular area? Like a regular shape of an area? A square, a rectangle, a circle, maybe an ellipse, we could work with that. A trapezoid, a triangle. Parallelogram?
Sure.
Your outer
Sure.
thing.
Surface area of a sphere, or of a rectangular solid, or of a triangular prism, or of, okay. You get the idea. Regular shapes are geometric figures, solids, whatever, from back in what, elementary math? Maybe not. Maybe math 6, math 7, pre-algebra, etc. Geometry for sure. Is this a regular, solid, geometric shape? No. Why? What makes it not regular?
The curve.
The curve. The A to B is fine. That's horizontal, and then the B height is fine. That's vertical. The A height is fine. But we do not have a function that will help us find the area when we have a side that is curved in any way other than a circle. In any way other than a circle. So our dilemma is we have an irregular figure. Now, if you just had some sort of irregular shape out in the world, you have to actually figure out a function that would map that curve. This one, we're saying there is a function that maps this side. So we know that much. But the problem is, how do we find the exact area that's shown? Well, we start with pre-cal. And in pre-cal, we say, hey, what's a shape, or I should say, we start with pre-calculus. Remember when I'm saying that, I'm not necessarily saying we did this in pre-calculus, I'm saying pre-before, right? So before calculus. Before calculus, well, we can't find the shape of that or the area of that, but what can we find the area of? A rectangle. Now, would that be a somewhat close approximation? Somewhat, but is it still pretty far off? Is there still a pretty good amount of air? Yes. So what would make it a little bit better? Well, pause. Hold on, pause. How would you find, hold on, pause. How would you find the area of this rectangle? I'm going to say n equals 1, and n is the number of rectangles that we're fitting in under the curve. Okay? So if n is 1, we're only fitting in one rectangle. You guys can see it right there. Area equals base times height. And how would I go ahead and plug into base times height using what I see up here? What would base be? The distance between A to B, which means the subtraction, right? B minus A. So instead of base times height, because I have a B in my picture, can I use length times width? Is that okay? Yeah. Okay. But same idea. So I have B minus A, that's going to be the base, that's going to be the length. What's the width going to be, or the height? Because those are horizontal.
If you have
Not
measurements,
division.
it would be easy.
You have all you need to denote what the height is. Plug
in A for X.
to what?
To
To the function. This is f of A, right? If I plug in, I get a height. I get a y value. So my base is going to be the change in x's. My height is going to be f of A. Does that make sense? Now, what if I drew the rectangle differently? What if I didn't draw it right there? What if instead, because there's technically always two ways to draw shapes under curves. Well, there are actually more than that, but two introductory ways. I could have also approximated using this rectangle. Once again, there's some error, so it'd be an over approximate. So you have an under with the one, you have an over with the other. But my question to you is, how would you do base times height with this guy?
G. Still
Still B minus A, but what's different now? Good. You guys see it? So I have two different heights I can play with, I can choose from. Now, that's if I was approximating with n equals 1. And once again, you could choose from the right or from the left. Sometimes like in your homework or in the group exploration, it'll say inscribed, like underneath rectangles, circumscribed outside. So f of a, since it was lower than the rest, is going to be an inscribed or an under approximation. F of b would have been circumscribed, so then it would have been an over approximation. Anyway, there were two different ways of doing it, but long story short, n equals 1, there we go. What if I wanted to fit in n equals 3? What would I do? 3 rectangles. You guys choose. It doesn't truly matter at the end of the day. Do you want to start from f of a and go from left to right, or do you want to start from f of b and go from right to left? Left to right.
That's how you read.
Wait a minute. If I want them to be equal, what would I need to do with b minus a?
Divide it by 3.
Split it into thirds, right? Okay. So I'm going to go ahead and have one rectangle. Question. Would I just keep this at the exact same height, or would that be the exact same thing as n equals 1? Okay, so I don't want to keep it the exact same as n equals 1. What could I do now that I've gone one interval of, you could say technically this would be a plus b minus a over 3, technically. You take a and you add 1/3 of this increment. Anyway, that's the x value. But wait a minute. I can reevaluate the height. So I can go ahead and find his f of a at that value. What am I doing? Eliminating some error. And then what can I do once I do, starting from a, doing 2 increments of b minus a over 3. It's nasty. I took this distance, I cut it into thirds and say, okay, add 1 of those thirds and add 2 of those thirds. And adding 3 of those thirds, you've gotten back to b. If I can go ahead and reevaluate again, my question to you is that area going to be a better approximation? Yes. Okay. This is what we're going to do in our group exploration. We're going to actually do some of the math with a specific f of x and with a specific number of intervals that I want you to fit in. And we're going to do an under and an over and see if we can guess what we would think the in-between would be. Does that kind of make sense?
Yeah.
We're going to do an under approximation, then an over approximation, then we're going to kind of guess. See if you can guess, and then we'll see how our calculator can do the calculus to actually solve what we do not quite know how to do by hand.
Will there ever be like an overestimation is better than an underestimation, or are they always equal?
Well, at the end of the day, just like with the secant lines, our goal isn't to stop with the approximation method, but to use it to get the exact answer. With the tangent lines, we take the limit of the secant lines and we get the exact. These ones, same thing. Whether you start with under or whether you start with over, at the end of the day, we can take the limit of both to get to the exact answer. So it doesn't truly matter at the end of the day, but when you're approximating, when you're being told to approximate, like on the AP, they say to use what they would call Riemann sum. We'll talk about it second semester maybe. When they instruct you, they're going to give you very precise instructions, and all they're going to ask you is not whether or not it is better or worse. They're just going to ask you, based on what they've given you, is it an under or an over? That's all you need to know how to determine. Now, there is a quick dilemma with this one. Because it is not strictly increasing, it's doing a little bit of increasing and decreasing. There is an under and an over portion. That gets a little bit messier. In your homework, you're going to see some of these where there might be some under and some over, and it's going to ask you to consider approximate as precisely as possible as to whether you think putting these together it would be under or over, but on the AP it's almost always strictly increasing, strictly decreasing. It will be really obvious whether it's an over or whether it's an under. Only in your homework will you be given some of those where it's a little bit of both and you have to kind of make a determination. What do you guys see on this one, just from the pictures that I fairly precisely drew? Is it going to be under or over? Yes, because look at that area. It's a number. Look at this area. Look at that area. Is the under going to be more than the over? Yes. So it's going to be an under at the end of it. Yeah.
What if, like for this graph, you connect the point, like point in the function, like the A value and the B value, and you connect and you draw lines.
Oh, the trapezoid?
No,
No, still a
so
rectangle.
over the.
Over here. Oh, if you come from this direction?
No, I mean like just draw a line through the 2 points and.
You can show me what 2 points you're drawing a line into.
So, like this line and this line, if you draw like a little.
Oh, trapezoid. No, it's okay. I couldn't do it. If I did that.
Yeah.
Yeah, it'd be another way of approximating. It would be called a trapezoidal approximation,
Okay.
but we're not using those to approximate right now, but we will. Trapezoidal approximations are good too, but the definition of the calculus, which is called an integral, the definition of an integral, which is the calculus way of solving this, to make the formula as easy as possible to take a limit, they just do rectangles, because rectangular areas, base times height, are easier than trapezoidal formulas, 1/2 base 1 plus base 1, or 1/2 base times height 1 plus height 2. So the idea is that the formula that we would need to take a limit of, even with trapezoids, still error, right? If we connect, this is what we call trapezoid, still error, so we would still have to do a limit. So they're like, okay, let's make the formula as easy as possible to do a limit, and that's why we do rectangles. Okay? How the areas would look on this one is you would have an A1 for the first rectangle, A2 for the second, A3 for the third. The bases, or the lengths, would be B minus A, but didn't we cut it into thirds? Does that make sense? And then the height, well, this one's going to be F of, I used A for the left. The base is going to be the same. It's going to be 1/3 of the distance, but then for the next one it was what? A plus, yeah, nasty, right? And then B minus A all over 3. I'm just starting at A because it's easier, and I say, hey, I need to add 2 of those thirds. So plus 2. B minus A.
Oh no. It doesn't look okay if there's no parentheses around the 2.
No parentheses on the 2. Then you put the 2 up top.
Yeah. Or you can put them individually in parentheses.
The other way I usually do it is way up here at the beginning. I say delta x, which is the base. I just call it B minus A all over n or 3. And I can just say delta x, 2 delta x, delta x, delta x, delta x. That's too snazzy. Anyway, that's the idea. I want you guys to practice it. You can. You should be using your Scratch. Not your Scratch, your workspace. There you go. I have to get that. You turn down. Use the workspace in the back of your spiral. Go ahead and label it. You're still in section 1.1, group exploration, part 2 for the area problem. I'm going to go ahead and make this bigger so you guys can see it. And you are, once again, you are drawing on the graph itself. If you want, you can get 2 different colors, because then you can show the ones that come from, you guys see how this comes from the left endpoints? And then that one comes from the right endpoints. You can use 2 different colors to get them both on there at the same time. But you're going to need to do 2 different calculations. What would the area be approximating here? And what would the area be approximating here? And how should you be able to do this? They gave you A. Well, 1 equals 0. What's A? 0. X equals 0. What's B? 1. How many rectangles are you fitting in? 1, 2, 3, 4, 5. You're fitting in 5. So you're going to have to follow what I did, but instead of doing B minus A over 3, you're going to do B minus A over 5. So you have to split up your X values into fifths. Now you could do 1/5, 2/5, 3/5, but who likes putting that in their calculator? Nope. So what's the decimal for fifths? 0.2, 0.4, 0.6, 0.8, and then at 1. That'd be easier. Ready, set? Go. See if you can follow my procedure with a specific example, getting actual numbers for approximations of the area. Yes, can I do one quick little help? Can you see the 5th rectangle on this first one? This is where you're going to start. Why can't you see it? What's the height if you start here?
0.
So 0 times anything is 0. So it technically is your first rectangle, but your first rectangle has an area of 0. Then go to the next one, then the next one, then the next one. This one, are you going to have a 5th rectangle?
Yes.
Yes, because it's 0. Okay, go.
Right here, Let's draw the graph 3 times.
Kiddos who missed class today, I will go ahead and try to illustrate based on the pictures because they're just kind of copying the pictures on the board. I'll try to illustrate what they were able to find in just a moment, but let me go ahead and pause and let them work for a little bit.
So that next one.
Just so you guys double check, keep working on what you're working. I'm just gonna start labeling a few things up here.
That's not a good thing. Oh shoot.
Did you get
I'm doing. For some reason I didn't put one
error
zero
0 2 0
That was a mistake. It doesn't matter. I'll just do the final calculation.
Oh, well, what's your factor?
The next one.
0.8.
It's like 3/5. No, 2/5.
Nothing.
I don't think that's quite 1/2. I think that would be an
Yes, because you
overestimation.
have to find the error. So 1, 2, 3. Oh wait, I don't have 5. So I got. Wait, hold on. So I got a 0.2. So that's that 0.2.
And the last one, that's like 2/3.
Oh, because they're all two.
You know what we're doing?
Oh.
Imagine all of these are 1/5, but all of them are equal to 1/5 the base. And I'm just approximating the height by what kind of looks right. The first one is 0. I don't know why I have one. Don't worry about that. Then the next one is 1/20th, and it barely exists. And then it was 2/5, 2/3. And that's to find the area of these ones.
Oh, I just 0.7 squared.
So when you add that up, errors.
That's why you skipped 7. Like, what did you do?
Me?
Yeah, you just said you just went
1 over
6.
100 plus
Okay, so that would be minus.
1 over 40 plus 2 over 25 plus 2.
But then it's still have. Then it's still have 0.7 0. It's still
Yeah, I got pretty much the same thing. Except you did rounded decimals, so it's, you know.
It should be 0.8 squared. Wait, hold on. Let me just make sure. It's just 0.64 times 2.
And make sure you're speaking in English in case people in your group that don't speak Chinese.
I speak.
I don't know, it should be.
What is it?
Maybe like let's see the pages there.
So,
Alright, Eris, now on to our next problem.
Oh,
So it's basically the same.
Yeah,
So 1 times 0.2
So
times
1
1.
is 1. Okay.
1/5 and one's number is.
Why did
I
you
say
say
it's 1. Eris, that's not six.
I know one. Well, no, but
1 comma 1. In fact, it is 1.
Because 2/5 is 0.4, but your base is still 0.2. Your base isn't changing in length.
Oh snap! You're right.
Okay, Eris. The next one.
So your base,
You wanna go
your
with
base
1/2?
stays at 1/5 instead
feel
of
like-
2/5, and it's
I feel like it is
at
1/2,
1/2,
and she's just
but
like it's just
only
not quite
still the same
perfect.
length.
You're right. Okay, if you guys don't mind peeking real fast
What's
at
0.8 squared?
hopefully the first one that you were trying. Right?
Yeah.
So this one over here. Why did I put 0.2 as the first piece of every single area equation?
The base. So
Because it's the base, it's how wide each of the bases are. Even though that's 0.4, 0.6, 0.8, remember it's 0.2 in between each one, right? Okay. So we took the entire 1 unit, we split it into fifths. So each base is 1/5. Why do I have F of written
It's
next?
0.6.
because you gotta plug in, which is
I have to plug in the correct point to get the correct height for my base times height for my height value. So on this one, what was the first height as you move from left to right?
That was 0.2.
No. 0.
Oh yeah. 'Cause you-
Why? If I zoom in on the picture, you guys see the first height? Yeah, because it goes 0.8, 0.6, 0.4, 0.2. It's hard to see, it's not even there, but it's 0. So, what's the next rectangle's height? Does it hit at 0.4 or 0.2? Hits at 0.2. The next one hits at 0.4, the next one at 0.6, the next one at 0.8. So I'm going to go ahead and plug in 0, 0.2, 0.4, 0.6, 0.8. Now we still have to actually do that, and up here at the front they were like, we plug in, right? Yes, you have to plug in. To who? X squared. You have to figure out what is the height at 0. Well, that one's easy, 0. What is the height at 0.2? What is the height at 0.4? What is the height at 0.6? I'll show that in my calculator in just a second. Have you guys gotten the next round? So how would I plug in the formula for the other rectangles? Coming from the other direction. What would my bases still be? Base is still 0.2 because I split it up the exact same way, so they have the exact same. But what's my first height? Look at the first rectangle. Does it hit at 0 or at 0.2? It's at 0.2. The next rectangle hits at point. The next rectangle hits at point. So we have 0.2. I'm going to go ahead and freeze the screen so you guys can't see what I'm doing, and I'm going to go ahead and plug and chug these whole expressions in one line on my calculator. Sorry, people watching, you can't see me freezing the screen, but you'll get to watch what I do to solve.
Instead of or no, times 0.2. Are we doing the other one?
Okay, sorry, what's happening over here?
You mind drawing that?
I've been through the whole
The
yes, paying attention to what we were
the
doing.
one where it goes above. You want to know.
So you can help Sandy caught up here by explaining what you're doing now.
Well, that would make sense. We're going to the one that goes above on every single one. It's in here. Actually, one's here. Okay, so it's still 0.2. So the first one.
See,
You guys should almost have your approximation. You're over and you're under, and then you're trying to think, can I figure out what might be in between?
If you did it correctly, can you just take the midway point between the two? Or like the average between them?
Seems like it, except if you look at the curve, there seems to be maybe more of an over approximation than an under. See what I mean?
Yeah.
Because if you were just to make one rectangle, it seems like the over would be higher than the under, so that's going to be a dilemma.
If you had an infinite amount of
There you go.
rectangles going on forever, then you could.
There you go. Hence why we need limits in calculus. Go team.
Or a lot of time.
A lot of time. And at some point it would be insignificant as far as the difference, right? Because you would have it correct to so many decimal places, but once again, do you really want to spend all that time? Probably not.
Better than 12th grade English.
What do you guys think? 0.24 and 0.44?
So you use instead of
Do you guys see how I put it in all at once? Why are they all squared? What was I doing? I was plugging and chugging to f of x equals x squared. Now, what if it was a worst function? A worst function. What if it was 3x squared minus 13x plus 1? Would you want to put that over and over and over?
Probably not.
No. So you would put that in your y equals, and you would use your y bars. Remember, y1 of 0, y1 of 0.2, y1 of 0.4. You could also shortcut the fashion. Do you guys know what I'm talking about?
Yes.
Those of you that took pre-cal with me, you definitely know. Those of you that don't, I could have put x squared into the y1, y equals. And then I could have, in these, I could have done shortcut alpha, trace. I could have used y1 of 0 instead of doing 0 squared. I could have done y1 of, now, is that really faster than just squaring it in this problem? No, it's not faster. But if it was a nasty function, would that be faster than plugging in? Oh, yeah. Way faster, right? Okay, so my approximations are 0.24 and 0.44. Why did I only write 0.2 once in regards to the base in my calculator? What did I do?
multiplied by everything.
I factored it out. Yeah. I factored it out, and it would go ahead and multiply into everybody. So I factored out the 0.2 from everybody, and I just said this guy plugged in, which was 0.2 squared, plus this guy plugged in, which was 0.4 squared, etc. So what would our approximation, what would we seem to think the area is?
0.3.
Yeah, maybe, right? We were like, area is 0.34, and this is our educated guess. This is our hypothesis, right? Now question. Can your calculator do area under the curve?
Yes.
Yes, but how? Putting a question mark. Integral. Now, don't worry. We haven't covered this. I haven't taught how to solve this, but I have taught how to approximate. But we're trying to compare to what the actual is. And I think in homework, there was a place where it was like, see if it's calculus, and if it is, maybe try to solve it. Yesterday, what did we see in our calculator as far as how to do slope of a tangent line? What was that again? Math, and it is f prime, which is the derivative. We saw this yesterday, how to find the slope of a tangent line. We can use derivative. Today, since I have the graph already, I'm going to make my window just be, oh, that would work. Okay. You can do this from the home screen too, but I want to show you on the graph because you can see it better. You can do second, trace. Do you guys see this little curly Q? Here's the derivative, dy dx, differential y over differential x. This is the derivative, kind of like what we did yesterday with d over dx. Number 7 is the integral, and it's going to ask you lower limit. Why? What's your a? What was the beginning of this region? X equals 0. What's the upper limit? X equals 1. Snazzy, huh?
Whoa.
Now, was it 0.34? No, and the reason was what I told Tyler. As you're looking at the curve, if you think one big old rectangle, an over approximate versus an under approximate, there's a lot more over than under. Even if you do it like in 2, the under error is going to be different than the over error just by nature of the curve. So that's why it wasn't perfectly in the middle. But we did have a pretty stinking good approximation just by splitting it into 5 regions, then over and the under and comparing. So the calculus, we're going to learn how to do this by hand and figure out that the area was 1/3 second semester. And we're going to apply it in all kinds of ways because this is just like a type of calculating, a type of something that we're able to do that can be applied to all these different circumstances. But anyway, you do not learn how to solve exactly without your calculator, but you learned how to solve exactly. And you learned how to solve by hand for an approximate, over and under approximation. Now, kiddos, in your homework, if you look on the back side, if you guys have your books, go and grab them out. I checked book covers yesterday, right?
Yes.
Good. There was a class I didn't. Austin was supposed to email me. Carrie, I know you emailed me. And then David, you email me? Are you guys emailing me? Do you have your book cover now? Oh. Email me. Put a reminder in your phone. Okay. In your book, David, look on with, if somebody in your group has it. Does Zach have his book? Yeah. Open up real quick to homework. I'm not going over specific questions today because it was not due today. We'll go over questions tomorrow. And guys, tomorrow we're speeding up. If you can think about what I just did yesterday and today, I basically showed you the questions we're going to be answering and using the rest of the school year. I showed you Calculus 1. Okay? So we illustrated Calculus 1. Now you need to know how to do all of this, but you learned how to approximate. You learned that Calculus will let us fill in the gap, will let us finish the problem, will let us get to the actual answer. But that's why I slowed down yesterday and today. Plus we had a test scheduled on staff appreciation lunch day and that kind of stuff, so now it's a day later. Anyway, that was not the reason why, but it was an added perk. Section 1.1, you guys know, 2.1. Oh, why am I in BC book? What am I thinking? It's 1.1. Sorry, guys. Why did I put you in BC? I don't know.
Yay!
Goodness.
Which one of us passed the calculus exam?
That's a big question. Okay. Section 2.1. I want you guys to look at a few things real quick in this section. Turn to page 124.
Oh.
We don't have a lot of time. I want you to quickly say 124, 125, 126, 127, 128, 129, 130.
Oh my gosh!
Did we take notes on every single thing in this section?
No.
No. It might be a good idea to skim this section because it does introduce a lot of ideas. I would skim this section. We only went over the two biggest ideas from section 2.1, but pause. On the front, you see with or without calculus, and you see secant lines. And then on the back, why am I not in the right one? This is AB. Stink-a-dink. Okay, pause. Sorry, you guys know if you started homework last night. On the front, with or without pre-calculus and secant lines. On the back, haha, what do you see?
Ah, shoot. Are you gonna have us do it?
Yes. Finish your homework tonight. You are ready. You are prepared. Now wait, it's not every single problem, right? Go back to your sheets online. Get out of here. I'll see you guys later. I'll be here after school if you have any questions. I will remember you guys are in CalcAB one of these days.
Oh. Oh no. Oh
You're
no.
trying to solve. Try to plug in 2. That's going to be 0 over 0. Okay, summer. You can also do what we did in our calculus. It's actually instead of show the how to use the derivative, you can put this as your y equals, and you can put this as your such.
Misty, I accidentally put down my Gov book in the